let's start again. So what we're doing here is now looking at acoustics. And what we want to do is to study acoustics in like in this room. What is the acoustics? How do waves propagate in this room? What are the equations that govern the propagation of these waves? So we begin with the set of equations of fluid mechanics. So we consider a fluid, for example, typically air, which is characterized by the P is equal to rho RT. It's a perfect gas or nearly perfect gas. And we assume also that the pressure can be represented in terms of the density and the entropy. This is it's very convenient. And we know how to write that law for air. It's written there. It's P is equal to rho gamma e to the S over CV. And this is of course, I'm not demonstrating that, but I think it's in your background. If it's not, you have to go and look why is it so, but it's simple. You can find that P over rho gamma is the isentropic. You see, when S is constant, you have actually P over rho gamma is equal to constant. Okay, so what are the basic equations that we start with? Are the Euler equations. This is the balance of mass, where you have the density and the velocity, and this is the divergence of the fluxes rho v. Then you have the balance of momentum, rho dv by dt plus v scalar gradient of v is equal to minus gradient of p. The other terms are neglected. And the third one is a writing of the equation of energy, but in terms of entropy. And when there is no viscous stress, now somebody asked me what we should consider the viscous stresses in the flow. In fact, only at the boundaries. You know, the boundary layer is important there where you have some viscous stresses. But in this case, they have very low effect on acoustic waves. So you can neglect viscous stresses and heat conduction completely when you look at acoustic waves. You don't need to keep them. So this is a way to write the equation of energy. I showed you that it comes out from the balance of energy that you can write, that is usually written for the internal energy. So you can write it like that. And what are we going to do now? We are going to expand these equations by assuming that all the variables are a mean and a perturbation. For example, the pressure is a mean pressure, P0, plus a perturbation, P1. And P1, which is associated with the acoustics, is very small compared to P0. Typically, for example, 100 decibels, when you know that 100 decibels is unbearable. You cannot listen to that. It's too much. It's 2 pascals. It's only 2 pascals. 2 pascals is 2 × 10⁻⁵ atmospheres. So it's very tiny. But the ear is perceiving very tiny perturbations. This is wonderful about the ear. It's a remarkable instrument. It loses its capacities as you grow older, unfortunately. But basically, it's absolutely remarkable. And even 2 pascals is too strong for the ear. 0.2 pascals is 80 decibels. Okay? So we'll look at that later. So these are very small perturbations. We are looking at very small perturbations. We can consider also that the velocity here will be small. Now, we will assume here first that there is no mean velocity, that there is no flow, and V1 is small compared to the speed of sound. We will assume that the density is equal to the density in this room plus a small perturbation, ρ1. ρ1 divided by ρ0 is very small compared to 1. And so what happens to these equations when we put this, these developments. So let's take, for example, the first one. Let's take first the last one. What happens to the entropy? The entropy says ds by dt is equal to 0. Let's assume that without perturbation here, rho 0 is constant, p0 is constant, so S0 is a constant. So if S0 is constant in the whole volume, you see that ds by dt is equal to 0. There is no change in entropy, so S will be equal to S0. So all these perturbations will be isentropic. Everything will be at constant entropy. All right? And what happens, for example, for the first equation? You take d by dt, rho 0 plus rho 1, plus divergence of rho 0 plus rho 1, and V1 is equal to 0. And so that equation, rho 0 is uniform, so d by dt of rho 0 is nothing. So d rho 1 by dt. And the second term, we have rho 0, which can be placed outside this divergence of V1. And then there is another term, divergence of rho 1 V1. And this is equal to 0. Now, this term is second order. This is a higher order term. It's second order. Because each of these variables are small, and so we can neglect that. And so finally, the equation of the balance of mass, in this case, which was here, is replaced, when we do the perturbations, is replaced by the following equation. We have here d rho 1 by dt plus rho 0 divergence of V1 is equal to 0. It's simpler. What happens to the equation, the balance of momentum? So we do the same here. So rho 0 plus rho 1 times dv1 by dt plus v1 scalar gradient of v1. This is the convective term. It is equal to minus gradient of p0 plus p1. And now, again, what we see here is that this is first order. This is second order, so we can neglect that. And on the right-hand side, what we can place is gradient of P1. And on the left-hand side, the only term that we have to keep is rho 0 dv1 by dt. Because as we multiply rho 1 by dv1 by dt, it's second order. And this one is even higher order. So the only term is rho 0 dv1 by dt. So the second equation becomes quite simple. It is rho 0 dv1 by dt plus gradient of p1 is equal to 0. So acoustics simplifies these equations. They become linear. And what happens now to the state equation? Now the state equation, P is equal to P of rho and S. What we've seen is that this expression can be written P0 plus P1. And we can expand the right-hand side around the zero state, the uniform state in this room. So it's P0 of P of rho 0 and S0 plus dp by d rho at S constant times rho 1. And one would have also a term dp by ds rho constant S1 plus higher order terms. And S1 is equal to 0. We've seen previously that S is equal to S0. There is no entropy fluctuation, so this term is 0. And this term here is P0. That goes away. And finally, what we get from this reasoning is that P1, so in this case, there is a direct algebraic relation between the perturbation in pressure and density. P1 is equal to dp by d rho at constant S, rho 1. And if you look at dp by d rho, the dimensions of this quantity is a velocity square. You know that the pressure has dimensions ml minus 1, t minus 2. The density has dimensions ml minus 3. And so this is L2 t minus 2. So it's like a velocity square, and this will be written c square times rho 1. And it turns out, you will see that c, actually this quantity dp by d rho at constant s, is the speed of sound square. It's the square of the speed of sound. It will become apparent. So let's call it c anyway. And so the third equation can be written here. It's P1 is equal to c square rho 1. All right, so this is what we have in the slides. You see, because the fluid is bivariant, we've shown first that S is constant, and we have this expression. So ds by dt is equal to 0, and finally S is equal to S0, and we then do these disturbances, just what I've shown here, and you take the first equation and the second equation, and finally we expand in a Taylor series the state equation right here, and we get finally this system of equations. So this describes perturbations in this room. The perturbations, the acoustic perturbations in this room are just described by this set of equations. It's very simple. It's much simpler than the equations of fluid mechanics. It's a subset. This is embedded in the equations of fluid mechanics. It describes the small perturbations of the equations of fluid mechanics. So now it is possible to actually reduce this system even more. So for example, we can eliminate the density and just keep the pressure in the first equation, the balance of mass, like that. And we have the balance of momentum, rho 0 dv1 by dt, plus gradient of p1 is equal to 0. But we still, if we want to calculate the density, it is related to the pressure. In fact, it is possible to visualize acoustic waves through their density changes by using Schlieren. If you have a sufficiently high acoustic level, you can actually use Schlieren, and you see the acoustic waves coming out from a loudspeaker, for example. It is possible to visualize acoustic waves because they change the density. Very small changes in density, that's sufficient, and you can actually visualize that. Very early in my career, we were doing experiments with a system like that. You had a loudspeaker here, and that was a cone, and the waves were coming out from this cone. And we set up a Schlieren system, and this was about 100 decibels here. And you could actually see the acoustic waves coming out through the density changes associated with the pressure. Not very large, because C is typically 300 meters per second square, and so you see that the level of the density changes is minute, but nevertheless you can see that. All right. So now, this is a second set, and now a third possibility is to actually take d by dt of this expression and take divergence of that expression and with a minus sign and just subtract one from the other. So what happens here? So the first equation is 1 over c squared d2p1 by dt squared plus rho 0 d by dt of divergence of v1 minus rho 0 divergence of dv1 by dt minus Laplacian of p1 is equal to 0. So these two terms are the same. You can interchange this, the time derivative and the divergence. And so the equation that is obtained is 1 over c squared d2p1 by dt squared minus Laplacian of p1 is equal to 0. And so, of course, you recognize, I hope you recognize the wave equation. This is the wave equation. It governs many waves. What is interesting is to see that acoustic waves are governed by that equation, but also electromagnetic waves are governed by the same equation. Of course, the velocity is different. The speed of light or the speed of traveling of electromagnetic waves is much higher than that of acoustic waves, but it's the same equation which governs the two types of waves, which is strange. And it is important to keep the other equation here, dv1 by dt plus gradient of p1 is equal to 0. This equation is important to represent boundary conditions. For example, a wall like that is rigid. You can shout in this place, the wall will not move. So v1 will be equal to 0 at the wall. Actually, the normal velocity at the wall will be equal to 0. You cannot move this wall by shouting in this place. So if you want to express that, it's through this equation. So this equation has to be kept. So it is possible to use this system, or to use that system, or to use the initial system there. So these are the basic equations of acoustics. So this slide just shows what is the speed of sound in air. The calculation goes as follows. C squared is equal to dp by d rho at constant s. So you find very rapidly that c is equal to square root of gamma r t0. and you take the values for the universal gas constant, 8,314 joules per kilomole per degree Kelvin. You take the molar mass of air, 29 kilograms per kilomole. You divide the two, it gives this magical number for air, 287 joules per kilogram per Kelvin. And when you plug that into the speed of sound, you get 1.4, this is gamma, 287, this is, and 298 for the temperature. And in fact, the 1/2 should be for the whole thing, not just for the last one. So it's 346 meters per second. So the traveling speed here in this room is about this value, 340 meters per second. So there is a delay. As soon as you have a traveling, you have a delay, and the delay is given by the distance divided by the speed. And of course, you can calculate the speed of sound in helium, in hydrogen, in whatever you want. Of course, the molar mass will change, and the speed will change with the, you know that people speaking in helium, you know, when you do some diving and you have a mixture of helium and oxygen, your voice is very different. You know, you speak at a much higher frequency. The resonances are different, and it's funny. All right. Are there any questions? Do you follow me? These developments are okay. I did them on the blackboard. You see, it doesn't take much time to get the right equations. So these are the systems that we've just seen, and this is the system where you have a second order equation. It's this wave equation. It's a hyperbolic equation in mathematically. It's very interesting to look at the solutions of that equation. And it's important to keep that to set up the boundary conditions. It's always, the boundary conditions will tell you things about the velocity. It's also important to look at what happens if you are in one dimension. And so this is what we are going to do for a few slides. We consider now these equations, but in one dimension. So in one dimension, you have just one velocity component. So typically, let's assume that we are in a duct like that. And the coordinate is x. We have a single velocity component, v. We have the pressure. And let's drop the 1 by just remembering that this pressure is a perturbation, the velocity is a perturbation. So what we have is ρ0 dv by dt plus dp by dx is equal to 0. And we have dρ by dt plus ρ0 dv by dx is equal to 0. So this is the set of equations right there. And it's also important to remember that P is equal to C square rho. And in this equation, we can write this one like dP by dt plus ρ0 C square dV by dx is equal to 0. So these are the equations. And of course, if we combine them and get the wave equation, we are going to get, in the same way, but in one dimension, we get an equation which is 1 over c squared d2p by dt squared minus d2p by dx squared is equal to 0. This is called the D'Alembert equation. It was written for the first time by D'Alembert. Actually, I had to give a lecture on D'Alembert, his contributions to mechanics. So I looked at the papers of D'Alembert. He was from the Académie des Sciences. And I looked at his paper on the vibration of strings. And you have that equation written more or less like that. It's not quite. And D'Alembert, so you have this is how D'Alembert looks like. This I put the picture this morning so that you know who is D'Alembert. So what D'Alembert did also is to find the fundamental solution of that equation. This equation can be solved completely. You can write down the fundamental solution of that equation explicitly. There is no, you don't need a computer. You can write it down explicitly. And the idea is as follows. You find that the equation, this wave equation, actually can be written in a factored form. The factored form is d by dx minus 1 over c d by dt times d by dx plus 1 over c d by dt of p is equal to 0. So it's possible to write that. And so you see that it's quite tempting to change variables and to say, let's consider a variable xi is equal to t minus x over c, and another variable eta is equal to t plus x over c. And when you do that, that is, instead of using x and t, you use these two variables, you get an equation d2p by d xi d eta is equal to 0. In fact, minus 4 times this. You can actually do that again as a homework if you want to do that. It's not too difficult. And then what you remark is as follows. You can write that d by dxi of dp by d eta is equal to 0. What does it tell you? It tells you that dp by d eta is not a function of psi. So you can say dp by d eta is only a function, let's call it g of eta. Let's put it like that. And now this equation tells you P will be the sum of g of eta, d eta, plus a constant, but this constant will depend on psi, so some sort of f of psi. So in fact, what you find is that the solution of that equation is formed by two quantities, two functions. Let's call that G1. So basically, P is equal to f of psi plus g of eta. That is, the general solution of the wave equation is any function f of t minus x over c plus any function of eta that is t plus x over c. This is the general solution of that equation. Was written for the first time in a different way. The derivation doesn't go like that, but he arrives to this result, t minus x over c and g of t plus x over c. So you know the general solution is of this form. And if you look at the velocity, so what is the velocity corresponding to this pressure? The velocity is obtained from that equation here. So you see, to get the velocity, what you notice is that the velocity should have the same sort of behavior. The velocity should be something like a function f of t minus x over c plus g of t plus x over c. Why? Because if you try to make a different, if you try to give a different shape in terms of t and x, you will not be able to satisfy this equation here. So you have to write something like that. And now the problem is, what is f compared to this f? What is g compared to this? So let's consider first this one. Let's assume that p is f of t minus x over c. And let's assume then that v is equal to big F of t minus x over c. So we have to plug that into the equation for v. So what we see is that rho 0 dv by dt is big F prime. F prime of what? Of the variable xi. And then we have here dp by dx. So this will put a minus 1 over c. And this will place here F prime. But F prime with respect to the variable xi is equal to 0. And as a consequence, we see that F prime is equal to 1 over rho 0 c F prime. So we can integrate that. And of course, in the integration, there is a constant, but this constant is useless because it doesn't represent a wave, a constant in the, so we can just indicate, this indicates that F is equal to 1 over rho 0 c small f. That's it. So the velocity corresponding to this pressure is 1 over rho 0 c f of t minus x over c minus, in fact, when you do the same reasoning for g, you find that there is a minus sign here, g of t plus x over c. So this is the basic solution in one dimension for the pressure and for the velocity. And this is what is done here. You see, I did the demonstration, but it's very simple to do it again by yourselves. And what is the meaning of these equations? Well, you can look at this diagram and take, for example, a function f, which represents a pulse. And you look at instant t1. Here is the pulse. And now we take at instant t2, the pulse will be displaced by c times t2 minus t1. So if you plot that at t1, it's displaced here and it's plotted here. So this is a wave which propagates on the right direction. And the other wave goes exactly backwards. And what is interesting is this quantity rho 0 c. You see, this is it appears here, it's the ratio between the pressure and the velocity. It gives you this ratio p over v. Let's assume, for example, let's take just the wave traveling to the right here. You see that p over v is 1 over rho 0 is rho 0 c. P over v is equal to rho 0 c. Well, the number is typically for air, rho 0 is 1.2 kilograms per cubic meter, and c is 340, so it makes 400. And the name of this unit, this has received a name. It's the name of Rayleigh. Rayleigh is one of the founders of acoustic theory. And so the impedance, this is what is called the acoustic impedance. You see this specific impedance for a wave propagating in the atmosphere here this is typically 400 real. You know that impedance is a very important quantity. It's important in electricity. What do we call impedance in electricity? A resistance, but it's the ratio between
the change of voltage divided by the change of current.
That's right. So Z is V over I. This is electrical. And the mechanical impedance, which is used by people in vibrations and so on, it's the ratio of force divided by velocity. And in acoustics, impedance, the acoustic impedance, is the ratio of pressure divided by velocity. So what you see here is that the force is pressure multiplied by surface. So here is pressure divided, so between this mechanical impedance and the acoustic one, there is a difference here. This is the area. In the loudspeaker, you have electrical impedances, you have mechanical impedances, and you have acoustic impedances. So in this area, when you are working on electroacoustics, on things like that, you find all these three impedances. The impedance is very important because it tells you what happens to when you, for example, put a pressure on something, will it move? This is the value of this P over V. Assume, for example, you have an injector, you put a pressure pulse on this injector. Will it continue to give V or will it give something different? So this is it's important to understand this notion of impedance. Let me give you another example of impedance, of the value of impedance in practical life. When you do an echography, who has been examined by the doctor with an echography? You have? You're the only one? You haven't had echographies for looking at anything? No? No, you're very healthy. Well, so you're the only one, basically. Yeah?
I feel really bad right now.
Yes? No, it's, well, for example, when you have a baby, usually they are inspected by echography. So the principle is as follows. You have your body here, and the doctor puts a probe, which is right here, which is formed by many little transducers and operates at 1 megahertz. This produces ultrasound, and the ultrasound goes into the body and comes back, and you make an image, and you have a beautiful image here. Now they are remarkable. You can say, for example, if the baby is a boy or a girl, so you can distinguish things which are of importance. But so what did the doctor do to have that operating well? What does he do? He puts on your body a gel. And why is the gel there? There is a gel right here. The gel is here to allow waves to propagate without impedance, too much impedance changes. Because if you had air here, the impedance would be 400. But the body is water, 85% water. And the impedance in the body is 1.5, is 1,000 kilograms per cubic meter, multiplied by the speed of sound in water, which is 1,500 meters per second. So it's, again, 1,000 times 1.5. So it's 10 to the 6. So on one side you have 10 to the 6. This is also about 10 to the 6. And if there was no gel here, there would be a very strong change in impedance and the waves would be reflected and nothing would propagate. So you need to keep this impedance essentially of the same order to allow the waves to propagate in the body and have a right echography. Okay, that was just to give you an idea of the physics of impedance. All right. So now we've started using these equations, and one of the possibilities is to look at a given frequency, not to look at all the possible waveforms, but to decompose the field in terms of frequency. So the idea here is to consider that we have a harmonic waves. Why is it important to look at harmonic waves? It's because, first of all, we are sensitive to frequency. For example, when you listen to me, you understand what I'm saying, but more or less. But in addition, you are continuously analyzing the frequency. You see, for example, if my voice was high, yeah, suddenly, oh, the frequency is different. Yeah. So you are very sensitive to frequency. And mechanical systems are very sensitive to frequency. You know that there are resonance frequencies. You look at the frequency of the vibrations. So everything has a meaning. For example, you are on a boat and you are seasick. Why? Because your basic frequency is 1 Hertz. And if the boat moves at less than 1 Hertz, many people feel sick. It goes up and down like that. Up, you are sick, because it's a question of frequency. So frequency is very important. So this is why we look at frequencies. And the way to look at that is to say, for example, pressure, which is a function of x and t, could be like that, will be replaced by something which will be a function of x and a frequency. It is useful, it's very, it's much more efficient to use complex notations. You know that it's much easier to calculate things using complex numbers. In this field, we have to do that. So when we write that, in fact, we have in mind that the sound field is the real part of this quantity e to the minus I omega t. But we don't have to put real part. We will do that afterwards. We will say, we do the calculations, and at the end, we take the real part, and we have the field. We have the, so this is the method. It's a very effective method in electricity, in electromagnetism, in optics, in acoustics, everywhere. So the velocity can be written in the same way. And the density will be also the same, but of course very seldom do we have to use the density. So the density is a function of position e to the minus I omega t. So when we do that, what happens? Well, we eliminate the time as soon as there is a time variable, d by dt, it becomes minus I omega. So for example, the equation of the balance of mass, rho 0, sorry, 1 over c squared dp by dt plus rho 0 divergence of v1 is equal to 0 will be replaced by minus I omega p omega. We put this symbol just to say this is the component at the frequency omega, the angular frequency omega, plus rho 0 c square divergence of v omega is equal to 0, and the balance of momentum, rho 0 dv by dt, plus gradient of P1 will be replaced by minus I omega V omega plus gradient of P omega is equal to 0. All right, and we can combine these two equations. We can actually take again, the divergence of this one, and we can take just the divergence of that one and combine with this one, and one find that by just combining that, Laplacian of P omega plus omega square over c square P omega is equal to 0. So the equation that is satisfied by each frequency component now, you see, by just combining these two equations and eliminating the velocity by taking the divergence of the second one, you get the Helmholtz equation. I thought I would look at the face of Helmholtz also this morning, so it's not in your slides, but it's in mine. And this is how he looked like. So Helmholtz was a very big scientist, a very, very big, he's known for many things. The Kelvin-Helmholtz, for example, instabilities. And this is the Helmholtz equation. This equation represents, governs waves, but this time harmonic waves, waves which are at a given frequency. They are governed, of course, by the wave equation, but when you plug in these expressions, they are governed by this Helmholtz equation, and it is usually one sets k is equal to omega over c. K is the wave number, and so the equation can be written Laplacian of p plus k square p omega is equal to 0. It looks very much like a simple Laplace equation, but with a term like that. So you have the addition when you have a wave. It's not anymore a Laplace equation. It's something which looks like that. So let's look at what happens to waves which are harmonic and which are in one dimension, because this is a simplification compared to what we did here. We just look at waves which are propagating in one dimension and which are harmonic. Again, that is very useful because in many practical situations you have ducts. And so you want to know how the waves propagate in ducts. So the equation is d2p by dx squared plus k squared p is equal to 0. Well, that's the wave equation in one dimension, the Helmholtz equation in one dimension. We can always put omega here, but this is a little heavy and we can take it out. And the equation for the velocity, the momentum equation, writes I omega v omega plus dp by dx is equal to 0. So these are the equations in one dimension for harmonic waves. Now the solutions of these, we know them. P omega is a to the ikx plus b to the minus ikx. And using the second equation, we find very rapidly that v omega is equal to 1 over rho 0 c a to the ikx minus b to the minus ikx. And of course, these things are multiplied by e to the minus I omega t. So again, you do the calculations using these expressions, and then you take the real part, and you have the field that you actually measure, or but it's very convenient to use these complex expressions. Let me show you one example, because you can think all this is useful, but how do you use that actually in practice? For example, let's assume that you have the very simple system. You have a duct. It's infinite, so it's already ideal. You think there are no infinite ducts, but very long ducts, a pipeline. And at the end of the duct, you place a piston, and you vibrate the piston. So you have this very long system. There is no termination to this system, and you have here a small piston, and the piston is moving with a velocity v of 0 and t. 0 is x is equal to 0, is equal to v0 cosine omega t. So you want to know what is the pressure that is produced and what is the velocity that is produced in this situation, in this duct. What is the pressure amplitude that is produced if you are given, for example, the velocity fluctuation? And the reasoning is the following. It's nicer not to work in this real thing, but to use the complex representation, because this can be written as real part of V0 e to the minus I omega t. Now, what can you say about the pressure? The pressure in this duct could be of two waves, but because the duct is infinite, one single wave is propagating. It's the wave that goes from here to there. And that wave is A e to the ikx minus I omega t. This is a wave which goes to the right. The other one, b to the minus I. In the previous slide, I forgot to tell you that one is the wave propagating to the right, the other one is propagating to the left, like before. And so we can say that pressure is like that. The other wave, which comes from there, doesn't happen because it's in an infinite duct. The velocity corresponding to this wave is A over rho 0 c e to the ikx minus I omega t. And now you can say this velocity, this is the velocity at all points, has to be equal to this when we are at 0. So what we have here is that A over rho 0 c e to ik 0, so e to the minus I omega t, should be equal to v0 e to the minus I omega t. And so immediately you get A is equal to rho 0 c v0. So the pressure field P is equal to rho 0 c v0. Afterwards, you think, well, of course, I knew it from the beginning, but here you have it directly coming out from equations. Yeah? And it's e to the ikx minus I omega t. And if you're putting a microphone, what you would see is, of course, real part of P, which would be rho 0 c v0 cosine of kx minus omega t. So for example, you put a microphone here, you would actually see a waveform which would be exactly what is there. The amplitude of that waveform would be rho 0 c, 400 times the For example, if the velocity is 1 meter per second for this piston, you would have 400 pascals. Yep.
Can you take that equation on the bottom of the slide?
Yes.
Equation on the slide.
Yes.
Can you graph it for some arbitrary time t on that picture you have on the lower left blackboard?
Yeah, you can. This is exact. Yes.
You graph that there.
Yes.
So it'll just like damp vibration.
No, it won't damp because you are continuously vibrating the piston, and it produces a vibration everywhere is there, and you go on forever. You assume that it goes from minus infinity to plus infinity. Yes. And on the oscilloscope, you would see just your waveform, and the amplitude would be given by rho 0 C V0, and the phases would be, for example, if you put two microphones, so why do you want to put two microphones like that? Well, one way to measure the velocity is actually to use two microphones. This is for example, we use that in the lab. Instead of placing a hot wire is a problem because many times they break, or many times you have, suppose you have a flow reversal, the hot wire doesn't work. You know, it works when the velocity is in one direction. When you put two microphones close to each other, you can use the equation rho 0 dV by dt is equal to minus dP by dx to actually deduce your velocity in a flow. You can use this acoustic method, detection of the pressure wave, to detect the velocity fluctuation. So anyway, let's come back here. You see the pressure is given by that, and the velocity is given by V0 cosine of kx minus omega t. So the velocity fluctuation is V0, and it has this shape, this space and time dependence. All right? As an exercise, what you could do as a small homework for tomorrow morning, yes, those who do the solution will have a plus. You will have a bonus. I don't know what, but a bonus. You can rework this problem, but as follows. You take a finite duct like that. You put a piston here. The piston is moving at velocity V0 e to the minus I omega t. And this is an open duct. And at that point, you can assume that the pressure is approximately equal to 0. In fact, that's not quite true. The open-end duct, the pressure becomes 0 at a certain distance, somewhere like that. But let's assume that it's at the end of the duct, you have P is equal to 0. So this is your problem. You have here a duct. This is the distance L. And the problem is calculate P of x and t and V of x and t. In this case, you have to use the two waves, and then you do all the little mathematics. It's not much, and you can calculate that and look at your velocity, look at the pressure, what happens to the velocity, or what happens to the pressure. It's already a nice little problem. Okay, so let's stop for, again, 15 minutes.